Hello everyone. Class 12th topic is nucleophilic substitution reaction of haloalkanes. First we need to understand meaning of nucleophilic substitution reaction. Those reactions in which strong nucleophile replace weak nucleophile. What are nucleophiles? These already we have understood in 11th class. Now how to decide strong and weak nucleophile? What are strong and what are weak? If nucleophile can donate electron easily, it will be strong nucleophile. And if nucleophile can't donate electron easily, it will be a weak nucleophile. For example, if I talk about nucleophilicity of iodide and chloride, iodide is a strong nucleophile, means its nucleophilicity is more, and chloride is a weak nucleophile. If I compare chloride with iodide. Reason is obvious. Iodine electronegativity is less, that's why it can donate pair of electron easily. Its hold on its electron is less. But chlorine, its electronegativity is high as compared to iodine, so chlorine atom is holding electrons strongly. It will not allow lone pairs to go for donation. That's why chloride is weak nucleophile and iodide is strong nucleophile. Now let's check in haloalkane how nucleophilic substitution reactions are happening. To understand the concept, first we need to understand in haloalkane who is nucleophile. Haloalkanes are represented by Rx, general formula Rx. R is alkane part, hydrocarbon chain, and X is representing halogen. R and X are connected through sigma bond. We know X electronegativity is more than R, means carbon. So these electrons are little toward X. That's why X is carrying extra negative charge because it is gaining electron of carbon toward themselves. Now because carbon is losing electron, so here we will have positive charge. So in Rx, X is working as a nucleophile and R is working as a electrophile. Now, if we know who is nucleophile, we can easily understand nucleophilic substitution reactions of Rx. Suppose Rx reacts with nucleophile and this nucleophile is strong as compared to X. What will happen? X will be substituted by nucleophile and X will eliminate out. Now how it will eliminate out? Bond will break between R and X because X is more electronegative. So when bond will break, electrons will go toward X. Now X will carry extra electron of carbon with it. That's why we will have -1 charge over there. Normally also when X is making a single bond, it already carrying a 3 pairs. After bond breakage, there will be 4 pairs. Nucleophile, as we know what are nucleophiles, they have a lone pair for donation. When X will bring electron from R will have a vacant orbital and nucleophile can make bond in that coordinate bond and R and nucleophile will join together. These reactions are known as nucleophilic substitution reaction. Here, this nucleophile is stronger as compared to X. Now let's check which reagents can do nucleophilic substitution reactions in Rx. Reagents like NaOH, KOH, silver oxide moist, sodium iodide, sodium alkoxide, (1° amine), 2° amines, potassium cyanide, silver cyanide, potassium nitrite, silver nitrite, silver salt of carboxylic acid, sodium hydrogen sulfide, sodium salt of thialcohol, lithium aluminium hydride. These reagents can provide nucleophilic substitution reaction of Rx. But how? Let's check. For example, NaOH. We know NaOH always break in two parts, Na positive, OH negative. OH negative is working as a nucleophile here. Means when our Rx will react with NaOH, OH is a nucleophile which is stronger than X, so OH will substitute it. ROH will generate, and Na, who is carrying a positive charge, X is carrying a negative charge, will combine together and will make NaX. Now you can check, after nucleophilic substitution reaction of Rx by NaOH, a new organic compound is generated, ROH, alcohol. These reactions are they have so much importance because after these reactions we are getting new organic compounds. One more example. For example, I am taking lithium aluminium hydride as a reagent. Suppose Rx is reacting with lithium aluminium hydride. So first we have to understand which nucleophile is generated by lithium aluminium hydride. The nucleophile is H negative hydride. So lithium aluminium hydride will provide H negative, and this H negative is stronger nucleophile as compared to X. Means hydride will substitute X. New compound generated will be RH, alkanes. Means from haloalkane we can make alkane by reacting it by lithium aluminium hydride. From haloalkane we can create alcohol by reacting it by sodium hydroxide. Similarly, suppose we have sodium alkoxide. So first we need to understand who is nucleophile and who is electrophile here. Na positive and O negative R. So this O negative R is nucleophile over here. Means when Rx will react with RONA, sodium alkoxide, this is the nucleophile we have which is stronger than X. So it will substitute it, and bond will be generated through oxygen side because oxygen have a lone pair for the donation. So OR and NaX will generate out. Now this is a new organic compound, ether. Means from haloalkane we can create ether by reacting it with sodium alkoxide. That's why substitution reactions are very, very important. Now with these reagents, different reagents, we can perform different substitution reactions. Like if I take KCN, potassium cyanide, so it always break into part K positive and cyanide negative. Now if it is reacting with Rx, so we know it is creating which nucleophile? Cyanide. Cyanide is stronger nucleophile than X, so it will substitute it RCN. Alkyl cyanides will generate, and this X will be balanced by potassium, KX. In this fashion, nucleophilic substitution reactions will happen. Now, the last point here. We know we have 4 types of haloalkanes: RF, RCl, RBr, RI. Who will show nucleophilic substitution reaction fast? Means out of these 4, which is most reactive toward nucleophilic substitution reaction? Reactivity order. Reactivity order towards nucleophilic substitution reaction. So reactivity order, if I write increasing reactivity order, the reactivity order will be this. RI. Iodoalkanes will be most reactive toward nucleophilic substitution reaction, and fluoroalkanes will be least reactive. Reason? Simple. During nucleophilic substitution reaction, this bond we have to break. And we have already discussed this bond is strongest because bond length is very short due to smaller atomic size of fluorine, and this bond is weakest because of the length due to bigger size of iodine atom. So while nucleophilic substitution reaction, it can break very easily. That's why the reactivity order will be this. Now in next video, we will understand mechanisms of nucleophilic substitution reaction. 2 mechanisms are there, SN1 and SN2. One by one, we will discuss both mechanisms. Thank you very much.